Good afternoon / morning, everyone. Welcome to another TACO sponsored webinar. My name is Brett Zerba. I'm an applications engineer with TACO, although most of you probably already know that. This is our sixth in a series of for our TACO University classes. Today's presentation is on self-sensing pumps, theory and applications. Now, this is relatively new. Well, we say that, but I guess it still is in our industry technology, and so hopefully you get a lot out of it. Our goal is to teach you more about how the pumps work internally and what they're made up of. I guess what the drive is doing. So before we get too far into it, if you can raise your hand so I can tell that you can hear us and see us. Okay, I see some hands going up. My friend Darren McPherson, he's already got a question. Oh my God, geez, Darren, give us a second. Oh, hey, he's just saying hi. All right, and so feel free to type into the question areas, um, uh, and we will work them in as we have been throughout the presentations. Rich Medeiros will be giving the presentation. Rich has done a lot of work with these self-sensing pumps. Spent some time in our lab at our facility in Cranston, Rhode Island, working on some of the drives. So he knows these pretty well. So make sure you ask some questions. He can get you some great answers. Since today's the last in the series of the 6 classes, tomorrow, roughly 24 hours after this class ends, you will receive an email with links to the 6 videos and to your PDH credit hours if you've attended all 6 classes. If for some reason do you have, if for some reason you missed a class and you need something, just send it in an email and we'll work getting you some PDH certificates. So please don't let that hinder anybody. So let's see. I think that's pretty much it. Thermal Appliance Company, TACO, 100-year-old company located in Cranston, Rhode Island, producing HVAC, mostly pumps, but tanks, many tanks. Thanks a lot. We have a welded products facility located in Fall River, Mass. It's about 20 minutes, 30 minutes away from our facility in headquarters in Cranston. So, and we are a worldwide company owned by the White family, 3rd generation, and senior management team is led by Cheryl Merchant, and the whole leadership team is doing a great job for TACO and continues to put us in great position to move forward. Other than that, I think we're all set, and you all know Rich, and Rich, take it away.
Thanks, Brett, for that introduction. A quick intro for myself. I'm Rich Medeiros, mechanical engineer here at TACO. I specialize in the engineering and design of HVAC systems. I've been with TACO just under 8 years. I can't believe it's been that long. And I've been in the industry a couple of more years after that, or before that? Before that, I guess, yeah. So I've been around for a couple of years. And I am a PE, and I spent the majority of my career working in consulting firms designing and engineering HVAC systems. So let's get right into today's topic of the self-sensing pumps. We're going to talk a little bit about what that's all about. So hopefully with a little luck, I'll be able to advance the slides here. Let's see what happens. Ta-da! Okay, so we're going to talk about system curves. Just a very brief introduction on system curves, pump curves, specifically how they relate to standard pumps and also self-sensing pump curves, and control curve options, and then questions at the end. So getting right into it, I like to start off with this little diagram here. And this diagram helps us understand a little bit about what I refer to as, oh, let me get the right pen color here. I always like to have red, Brett. Choose, there we go. Okay, so right up here it says conventional sensor type system, and that's what most people are familiar with. And what does that mean? Well, that means that we have in this very, very simplified system we have a differential pressure transmitter. We're actually measuring the pressure differential across the most remote part of the system. And we're sending that information hardwired over to a controller. And that controller has some kind of control logic. In this case, it's saying, look, I want to have a pressure differential at the differential pressure transmitter location, have a set point down here of 17 feet. And then what I'm going to do, since I'm the controller, I'm going to send a hardwired signal to the variable speed drive. And it works like the following. It says, okay, if I have a 17-foot set point, as these valves begin to open, the pressure differential is going to drop. The controller is going to say, hey, wait a minute, I'm not maintaining my 17 feet, so I need to speed up the pump by sending a hardwired signal to the variable speed drive on the pump, and that'll speed the pump up, and I'll get back to the pressure that I'm looking for. Now, as the valves begin to modulate closed, the differential pressure transmitter sees an increase in pressure, and the controller says again, hey, wait a minute, I'm no longer at 17 feet. I need to slow the pump down, so I'm going to send a signal over this wire and tell the pump to slow down. That's how a conventional sensor type system works. And generally speaking, you need to have a differential pressure transmitter, a controller. It has to be hardwired between those two devices. And then you need a control signal, generally a 0 to 10 volt signal out to the variable frequency drive to maintain or change its speed based on what kind of pressure differential you're looking to control to. So before I go on any further, we want to start here because we want to start with a basic understanding of what a conventional sensor type system is. So do we have any questions out there, Brett, from anyone that says?
Actually, we do have a great question from Lewis. How do you calculate the pressure differential set point?
That's excellent. The pressure differential is made up of 5 components. So in this case, the flow, let me erase some of these lines here so that I can draw some new lines in here. So if you'll notice, the pump supply water is going down this line right here, and then it gets to this point. The flow continues along, goes through the terminal device, in this case a fan coil, a control valve, the bypass is closed, so then it goes across here. So we're measuring the pressure differential. And what are we actually measuring for the pressure differential? We're measuring the pressure drop at the maximum flow for the terminal unit for the following 5 major components. And that includes the fan coil itself, which is usually the coil inside the fan coil. It includes the strainer, the balancing valve, the control valve, and the isolation valve. And at the design flow, let's just make up a number and say we need 10 gallons per minute at this terminal device. And we would calculate what the pressure drop would be for each one of those 5 major components. And that would be the pressure that we're trying to maintain at the most remote point with our differential pressure transmitter. Hopefully that answered that question.
I'm sure it did. Here's another great question that I know you like to answer. Can the differential pressure transmitter be located near the pump?
And the answer is no, because if you locate it near the pump, then you're only measuring the pressure differential across the pump. You're not taking into consideration the increase or decrease in pressure differential of the system as the load changes. And if you measure it across the pump, for all practical purposes, you turn the pump into a constant flow device or constant speed device. So you need to measure it at the most remote point.
Good stuff.
Any other questions, Brett?
I think we can move on right now.
Okay. So that's how a conventional system works. So what we're going to do next is we're going to say, okay, well, I understand how a conventional system works. And we're going to now talk about a self-sensing pump that does not use a pressure differential transmitter. It does not have a hardwired control signal to the controller. There is no controller external to the variable frequency drive, and there is no hardwired signal that goes to the variable frequency drive. All you have is the pump, the motor, the drive, You put that into the system, you press the, you power it up, you press the on button, it knows exactly what to do. As the valves open and close, the pump increases and decreases its speed automatically. So that's how we're going to talk how it accomplishes that. So let's erase some of these lines here and go on to the next slide. Okay, the first thing we want to talk about is, let's say we have this oversimplified system here. Somebody has figured out that it's a 150-ton system. They did some calculations, and they also selected a 12-degree delta T, and it's a chilled water system. Ours is very, very simple. We have 5 fan coils. Each one has a 2-way control valve, with the exception of one of the units has a 3-way control valve. This guy right here is a 3-way control valve to maintain minimum flow. And with a 12-degree delta T, that means we need 2 GPM per ton. So if you multiply 150 tons times 2 GPM per ton, that comes out to 300 gallons per minute. Now, someone has to do a pressure drop calculation to find out how much pressure we need to get to the most remote point. And in this case, we calculated it to be 53 feet. We're going to talk about that in a little bit more detail. Okay, so now we have the design operating point of 300 gallons per minute and 53 feet. Let's plot a system curve on a flow chart. Let's go over here, erase this, and then go to the next slide here. There we go. Okay, so we are going to use this equation right here that says that if we're looking for the final pressure, I'll get my pointer again going here, looking for the final pressure, in this case H2, we multiply the initial pressure times the ratio of the flow squared, the final flow divided by the initial flow squared. And in our case, we started off with 300 gallons per minute and an initial pressure of 53 feet. And if we put that into a little spreadsheet format, it looks a little bit like this. So here's our design condition of 300 gallons per minute. Grab my pen. 300 gallons per minute at 53 feet. Now all I have to do is plug in these different values and I'll get the, plug in the different flows, and using this calculation formula up here, I will get the different pressure differentials. And if I plot that on a curve, on a chart rather, where the x-axis or the horizontal axis is in flow in gallons per minute, and the y-axis or the vertical axis is in differential pressure in feet. And if I plot that, I start with my design operating point. That's the 300 gallons per minute at 53 feet. And I use this equation in the upper left-hand corner. I create the table, and then I just plug in these values, and then I wind up with this curve, which is called the system curve. And in our example, the system is a closed loop pressurized system. And so therefore, because it's a closed loop pressurized system, it starts at 0 flow and 0 pressure. And actually is the right half of a parabola. So that's what a system curve is all about. If the pressure differential in the system is greater than what we had anticipated, the system curve bends upwards to the left. If the pressure differential in the system is less than we anticipated, it bends downwards to the right. And that pressure differential can fall along a vertical line. And so I just throw in a vertical line here so you can see what that looks like. So if in fact the pressure, instead of being 53 feet at 300 gallons per minute, is greater than that, perhaps it's over here somewhere. I'm just going to kind of put a dot up here. Maybe that's like 90 feet. So then I would draw a new system curve that would come up here and kind of bend upwards to the left. You get the general idea. Now, if in fact the pressure differential was not, again, 53 feet, maybe it was less than that, maybe it was 30 feet down here, then I'd have a system curve that bends downwards to the right. Kind of get the idea. So any questions about the system curve, how we generate it, and the effect of the pressure in the system causing the system curve upwards to the left, or bend, causes the system curve to bend upwards to the left if we have more pressure, or downwards to the right if we have less pressure?
No questions pertaining to the system curve. I got a couple questions, but we'll get those at the end.
Okay. So now let's go on and see what it takes to generate a conventional pump curve. So getting back to our pump curve, here's what we do. Now, most people might think that pump curves are created mathematically, but they're actually not. They're created by measuring the pump performance in a mechanical test lab. So TACO has a world-leading mechanical test lab physically located in Cranston, Rhode Island, and we are certified by the Hydraulic Institute. They come out, generally, they come out every year around December with a team of people that go through a checklist, and then they issue our certification. But last December, we had such a high score on our certification that they gave us certification for 2 years instead of 1. Excuse me, 1 second. I had to take a little swallow of water there. I'm losing my voice. Okay, so in this case, you can see a photograph of our mechanical test lab, and one of the technicians is setting up an end suction pump for testing. Now, he hasn't quite connected all the piping and all the components, so I'm going to kind of just walk you through what he needs to connect. There are 4 pieces of information that we need to collect in the test lab. We need to collect the flow in gallons per minute. We need to collect the differential pressure across the pump. That's the difference between the supply pressure and the suction pressure, or the discharge pressure and the suction pressure. And he needs to measure the horsepower. If you'll notice, the electric motor down here, let me get my pen again. The electric motor down here is not connected to the pump yet, and that's because the technician will eventually connect the device which will connect the motor shaft and the pump shaft with a device called a torque cell. It'll fit right in there. And that torque cell allows us to measure the shaft horsepower, the input power to the pump. Then we're going to measure the pressure at the suction somewhere here on this pipe. And then on the discharge, we'll measure the pressure up here on this pipe. Now, what you don't see in this photograph, I'll show you another photograph, is that there will be a flow meter that can measure the flow in gallons per minute. So now we have the 4 pieces of information. We have the flow in gallons per minute, the suction pressure, the discharge pressure, and the power input to the pump shaft. So what happens is that the water flows into the pump this way, comes out vertically, continues down this pipe over here, and then this valve, this manual valve, is a control valve. It's actually a manual control valve. That's important. We'll see why in a minute. The water continues across this pipe, goes through the wall, enters these buffer tanks, and each one of these is 10,000 gallons, comes out the top, and eventually, once all the piping's connected, goes right here, and then there's a flow meter. I'll just put FM here, that measures the flow in gallons per minute. And that's, you can see the arrow here. And that's how we measure all of those 4 different components. So I got a couple of other photographs to kind of make it a little easier to understand. So here is another pump that's being tested. This one is not being tested for performance. I'm sorry. This one is not being tested for performance. It's being tested to certify. This is called a certification test as opposed to a performance test. And the reason I know that is because we don't have the torque cell between the electric motor and the pump. So this is really being certified for customer, but you can see a little bit more information in terms of how we make our connections for our instrumentation. This blue guy way back here on this pipe is where we measure the flow in gallons per minute. This yellow pipe is measuring the suction pressure. This red pipe is measuring the discharge pressure. And because this is for certification, we're not measuring the actual power input to the pump shaft. We're measuring the total electrical power input and correcting for the motor efficiency. Okay, so now that we have a better idea of all of that kind of stuff, let's see how we collect that data and what we do for it. So I have a little diagram that kind of emphasizes the piping arrangement. So here shows a little bit clearer on what we've got going on. We're measuring the suction pressure over here, measuring the discharge pressure over here. We're actually opening and closing this control valve manually, and the water is going to flow through the buffer tanks and then through our flow meter, and that's where we get our 4 independent readings. But in the pump world, we don't actually publish the suction pressure and the discharge pressure. We publish the difference between these two values. Now, let's assume that the discharge pressure was measuring 20 psig. Let me put a 20 over here. And the suction pressure was measuring 10. So 20 minus 10 would obviously be 10. And that's psi. However, in the pump world, rather than publishing the differential pressure in pounds per square inch, we publish it in feet of water column. So the conversion is 2.31. Boy, that's a bizarre looking tube, Brett, today. 2.31 feet of water column. And in the pump world, we actually don't write the words water column. We just say feet is equal to 1. Boy, my writing skills today with my mouse are not that good. 1 psi. So let me repeat that. It's 2.31 feet equal 1 psi. So if we measure the differential pressure of 10 psi, then we multiply 10 times 2.31, and in this case, it would be 23.1 feet. 0.1 feet. And the term that we used in the pump world is called head. H-E-A-D, and head specifically means the differential pressure across the pump. Okay, so we collect all this data, but before we go on to what we do with that data, any questions out there, Brett, that we need to answer?
There was a question about the bypass. Would the bypass be a two-way valve with pressure sensors or a pressure relief type device?
You could use a bypass, but when it comes to self-sensing pumps, we recommend three-way valves. Three-way valves are much simpler. The self-sensing pump reacts better to it. A differential pressure bypass is rather complex and the control strategies tend to be a bit cumbersome. So we recommend three-way valves in lieu of bypass for self-sensing pump designs.
Good stuff. Good stuff.
Good stuff, cheap. Building 19. Okay. All right, so let's go on to the next piece. Now we've collected our data from the laboratory, and for this particular example, let's say we're doing it for a very specific pump. In this case, let's say we collected the data for this pump here, KS model 4009, where the test data is specifically at 1760 RPM. We'll talk about that in a minute. We start off the test by installing the largest impeller diameter. In this case, it happens to be 9.25 inches. And the very first thing we do is we close that manual control valve until we get 0 gallons per minute. And we want to measure the differential pressure across the pump. And remember what I said a minute ago, that's called head. And we measure it in feet of water column, but we just use the word feet in the pump world. We don't actually say the words water column. And we get a pressure differential at 0 flow. We have a very specific name for that data point, and we call that the shutoff head. So the shutoff head occurs for a given impeller diameter and a given pump model, in this case, a 4009, and a given pump speed, and a given pump impeller diameter. You only have one unique shutoff head. In this case, at 0 gallons per minute, it happens to be approximately 84.5 feet of water column. The efficiency means nothing at this point because the pump is not doing any work, so this is a meaningless number. However, the horsepower is important because this is how much power the pump is consuming in order to get 0 flow and 84.46 feet of head. And since it's not doing any work, then all of that energy is being converted into heat. So one thing that you do not want to do is run a pump for any length of time in a shutoff head condition, because you'll generate heat and eventually, in a fairly short period of time, initially destroy the pump seal, and then eventually you'll destroy the pump. So it's important, if you collect that shutoff head data in the field, you only take a couple of seconds with the pump flow at 0 gallons per minute. Okay, and then we collect the rest of the data as we go down here. And the thing that's important to recognize is that as the flow increases, we go from around, say, 0 gallons per minute up to 650 gallons per minute, look what happens to the horsepower. The horsepower also increases. So there's a relationship between horsepower and flow. And we'll talk about that in a little while. Now, once we collect the data at 9.25 inch impeller diameter, we stop the test, isolate the pump, we take the pump apart, and we take out the 9.25 inch diameter impeller. We install the next size down, in this case 8 inches, and then we repeat the test data. And then we disassemble the pump one more time, put another impeller in this case 6.75, and we repeat the test to collect the data. So that's how we collect the pump data. What do we do with this pump performance data? Well, we plot it on a curve. So let's go to the next slide and take some of the data for an 8 inch diameter impeller, move it over here to the left. Now we're going to plot it on that same chart that we plotted the system curve, only in this case, we're going to start off at 0 gallons per minute. I'll grab my pen here. At 0 gallons per minute, we have roughly 60 feet. So there's 0 gallons per minute, roughly 60 feet. I'll put a data point right up there. 0 gallons per minute, 60 feet. There's the first data point. And then 100 gallons per minute, roughly the same, 60 feet. There's another data point. 200 gallons per minute at 58, should be roughly here. 300 gallons per minute at 53 is 55, 3 is right here. 400 at roughly 43, 443 is roughly there. And the last one, 500 at roughly 27. So there's 500, roughly there. I connect those diamonds with a smooth curve, and lo and behold, we now have the infamous pump curve. So the pump curve shows the relationship between the flow in gallons per minute and the differential pressure in feet, known as head of water column. Feet of water column is known as head in the pump world, and that's the differential pressure. And there we have a pump curve. Okay. Any questions about that?
Nope.
Okay. So now let's try to figure out what happens when the pump curve intersects the system curve. And we are the pump curve. That's this line up here. Let's just kind of highlight that. Here's the pump curve, and here's the system curve. And where the pump curve intersects the system curve, that's where the pump operates in the system. As the valves begin to close, the system curve bends upwards to the left and it rides the pump curve. So the system curve bends in this direction and creates a new system curve, and we call that riding the pump curve. If the pressure differential, because the valves are opening, decreases, then the system curve bends downwards to the right, and we ride the pump curve in this direction. So if this was the system curve over here, let's kind of extend that little arrow up. Then this is where it would be riding on the pump curve. If the pressure was less, this is where it would ride on the pump curve. Now, at one time in history, we didn't have variable speed pumping. We just simply allowed the two-way valves to open and close, and then the system curve would, we used to say, would ride the pump curve up and down. And that worked reasonably well as long as you didn't have major pressure differentials in the system, and it didn't save a lot of energy. So we're going to talk a little bit now about self-sensing pumps. And how do we generate the data for self-sensing pumps? Any questions, Brett, before we go on to test data for self-sensing pumps?
Well, there's a question in regards to the piping configuration in our test lab. In the pump test piping configuration, the pressure taps are located in the piping away from the pump. Using the flange taps in a real system, what is the difference in field testing, if any?
That's a great question. So when it comes to laboratory data, let me go back to the photograph here. make it a little easier. If you'll notice on the suction side of the pump, let me kind of point things out here. On the suction side of the pump, we have a minimum of 15 pipe diameters, and you can barely, this yellow tubing is connected for the suction pressure reading. You can see it a little bit easier here on the discharge where this red tubing is connected. And the pressure drop between the flange connection and the straight run of pipe, remember this is the same as the diameter of the outlet, it's negligible. So in laboratory conditions, we have very precise control conditions for the inlet conditions and the outlet conditions. And so the pressure at the pipe is the same as the pressure at the flange. Unfortunately, in the field, we don't necessarily get these kinds of nice 10 to 15 pipe diameters at the inlet and 5 to 10 pipe diameters at the outlet. And so we have to measure the pressure when we're in the field at the pump flange itself. And that's the most accurate place to measure it in the field. But in the laboratory, we measure it at the pipe. Hopefully that answered that question.
Good answer.
All right. So let's continue on here. Let me just go down to where we get into the self-sensing pump. So when we talk about a self-sensing pump, in a moment I'm going to talk about collecting the data in the laboratory. But I want to point out that the self-sensing pump includes multiple components here. A self-sensing pump includes the electric motor, that's the guy in the background here. It includes the variable frequency drive, that's the gray guy in the front, and includes the pump, that's this guy right here. Now the one that's in the foreground is a KS, it's a KV. So this guy is a KV, that stands for close coupled. And the one in the background, it has the same thing. It has the electric motor, it has the drive, the smart drive, and it has the pump. But what you can see, it also has this adapter, and this adapter allows us to have a coupling. So this is called a split coupling. So the one in the foreground is the close coupled, and one in the background is the split coupled. But when we think of a self-sensing pump, we think of all three components working together in concert with each other. They don't have to be connected like they are shown here where the variable frequency drive is physically connected to the pump. This could be remote mounted and mounted on the wall somewhere, but all three components work together as a single unit. And we test them in the laboratory as single operating units. So this is what the test data looks like in the laboratory. It's very, very similar to the test data that we collected for a standard pump, only in this case, we're collecting the data, we're collecting the data at a fixed impeller diameter, in this case 7.5 inches, but we're doing it at different speeds. Instead of 1760 RPM constant speed, we're doing it at a maximum speed of 60 hertz. And if this happened to be a 1760 RPM pump, 60 hertz would equal 1760. We also collected at 40 hertz and at 20 hertz. Now, in reality, we also collected at intermediate speeds at 50 hertz right here, but I didn't put that in the presentation, and also at 30. So we do it at 5 speeds. We do it at 60, 50, 30. Did I screw up, Brett? 60, 50, 40, there it is, 30 and 20. So 5 different speeds, and we collect the data. Typically, we take 20 data points at each speed, so we have a total of 100 data points. And again, as I mentioned a moment ago, there is a relationship between the flow in gallons per minute. As the flow increases, the power increases. And that holds true for each of the individual speeds. So once I have collected this data very, very accurately, I now have a relationship between speed, power, I'm going to circle one of this, flow, and head. And since the variable frequency drive, the self-sensing drive itself, is an electronic device. It can easily keep track of its own speed and its own power consumption, and it looks up the data that we provided after taking careful measurements in the laboratory. We call it lookup data. So this data that was collected in the laboratory is then placed inside the drive. We actually physically type it in using a computer, and we type in all of the data, and then from that point forward, the software knows exactly what flow and head it's producing because it can easily measure its own speed, because that's an electronic piece of information, and its own power consumption. It looks up the other data that we stored into the drive. And that's fundamentally how a self-sensing pump operates. It knows its own speed, it can measure its own power, and it looks up the flow and the head. And it always knows where it's operating. In a minute, we'll talk about how that translates into how it operates in the system. But before I go any farther, this is an important place to stop because this is fundamentally how a self-sensing pump works. Any questions out there, Brett?
No, I'm surprised there's no questions. So if the horsepower is 1.47 and the speed is 40 hertz, I guess the GPM is a 143.507 and the head is 24.5.
Right. And the pump can keep track of its own speed and its own power consumption. It simply looks up the data that we previously stored inside the computer, inside the drive. So that's how it works. It's as simple as that.
Here's a question did pop up. Is every individual pump tested?
No, only a family of pumps are tested. So in this case, it's a KS model 4007 with a 7.5 horsepower motor and a 7.5 inch diameter impeller. So once we test it for that pump and create the accurate data, then all the other models that are identical with the same impeller diameter, same horsepower motor, have the same characteristics. Now the characteristics can vary as much as 2 to 3%. But in terms of the overall operating characteristics of the pump, motor, and drive, it's insignificant. If you want, by the way, if you specify a self-sensing pump, you can have it certified, and that means that we would take it off the assembly line and put it physically in the lab. There's an extra cost for that, for having the pump certified, and some people not only want it certified, but they want it witnessed. So a witness is the same as a certification test, only someone sends a representative to the factory to witness the actual certification. And we actually give them a certified curve that says the pump operates in accordance with the measured data in the laboratory.
So what is the lowest speed the motor pump can be worked at?
In a self-sensing pump, we do not recommend that we go below 20 hertz. So that's the minimum speed, which is 1/3. If the maximum is 60 hertz, the minimum speed is 20 hertz. So 1/3 the maximum speed is the slowest we recommend that you operate that pump. The self-sensing pump, by the way, physically comes from the factory with a limit of 20 hertz at the lower end. So if you change those parameters, then essentially you're operating the pump outside of what the factory recommends. Okay, so now let's take a look at our system curve one more time. This system curve is the same one I showed you earlier with all the valves 100% open. As the valves close, the system curve bends upwards to the left, so we get multiple system curves depending on valve position, until we get all the valves closed with the exception of the three-way valve where we maintain minimum flow. Now, as I said before, if we overlay the pump curve on the maximum system curve and the minimum system curve, as those valves begin to modulate closed from the full open position, it's going to start moving from this point here, and it's going to ride the pump curve all the way till we get to the minimum system curve. And if it happens to be modulating control valves, you can think of it as almost being infinite in terms of the change. We know in reality it's not infinite, but it's fairly close. Okay, that would make the system self-sensing pump relatively energy efficient, but I mean, you would save some energy, but it's not very energy efficient. So what would be nice is if we could change the speed. At the same time, we're changing the valve position. So instead of running constant 60 hertz, we're going to actually change the speed of the pump from a maximum of 60 hertz to a minimum of 20 hertz. And what we're going to do is we're going to go from this maximum operating point here, 60 hertz with all the valves open, down here to 20 hertz with all the valves closed with the exception of three-way valve. And then we're going to connect those lines with a smooth curve. And we're going to call that a control curve. So I'm going to erase that gross line that I drew and have the control curve plotted out for you. Okay, so again, the control curve represents where the computer is asking the pump to operate between its maximum speed and valve open position to its minimum speed and valve closed position with the exception of three-way valve. And the computer is going to force the pump to stay on this red line, which emulates what a differential pressure transmitter does in a conventional control system. So this, in a nutshell, is how the self-sensing pump functions. It controls the speed of the pump, the self-sensing variable frequency drive with its computer and its software forces the pump to stay on this red line. And all we need to know to plot that curve is all we need to know is the design operating point out here and where it intersects the y-axis called the control head back here. And the control head, you can think of the control head as the minimum pressure required to maintain flow at the most remote point in the system. Okay, because it's controlled by software, we not only can have a variable flow, variable speed functionality, but we can also have constant flow, variable speed. And the third mode of operation is to have constant pressure differential and variable speed. All three of these control functions are embedded in the drive. So when you specify a self-sensing pump, you can tell us whether you want variable speed, variable flow, or you want variable speed, constant flow, or variable speed, constant differential pressure. The default, when it leaves the factory, is variable flow, variable speed. And that's where you get the control curve that goes from minimum to maximum. You can also, in the field, you can disable the self-sensing function and land an external signal of 0 to 10 volts, and the pump will operate as a conventional differential pressure pump system. Some people actually do that. They'll buy a self-sensing pump and they'll operate it with an external control. And when they do that, they're actually using the information that the pump has available in terms of its flow and head, power and speed for a building automation system information, but they're not using the self-sensing function. They're almost using the pump as a flow meter that they can measure the data. But the majority of self-sensing pumps actually, let's go back here. Sorry, went in the wrong direction. The majority of self-sensing pumps are sold for this basic functionality, where you have a variable speed pump in a two-way valve system, and you're varying the speed of the pump as a function of valve position without any external control components. There's no differential pressure transmitter, there's no wiring, there's no controller, there's no control signal. It's just the pump motor drive assembly. Put it into the piping system, power it up, press the button, it knows exactly what to do. Any questions about how a self-sensing pump functions?
Actually, we have a question. If you can go back to your slide that shows the different speeds in the table,
Yep.
yeah.
Go ahead.
So, do you not end up with crossing curves? For example, at 60 hertz, at 3.19 horsepower, you get 56.6 feet. There might be a point at 50 hertz where you have 3.19 horsepower that would correspond to a different head GPM.
That's true, but not at the same speed.
So it measures both.
For each unique speed, there's a set of data. You could have repetitive data, but not at different speeds. I'm sorry, let me rephrase that. You could have repetitive flow and head data, but it would be at a different speed. And the software is smart enough to know that it's at a different speed, and so therefore it has different data it's supposed to look at.
This is a common question as well. How accurate would you say the flow value is compared to a traditional DP sensor system?
The flow values are within 3% of the published values.
Good stuff.
Any other questions out there?
Actually, I think you answered this one, but this is probably a good one to re-answer. In the menu of the drive, is it possible to change the self-sensing operation from constant flow to constant head, or vice versa?
Yes. Through the keypad of the drive, you can select the different modes of operation, and you can also change parameters. So the instruction manual that comes with the variable frequency drive goes through all of the settings that are available and how you can change them. So there's lots of flexibility in how you set up the drive. You can take it out of the box, put it into the system, and just turn it on. It knows exactly what to do. If you need to modify it or customize it for any reason, you also have that ability to do that.
Good stuff. Somebody is asking for a little more definition of the control head.
Control head. That's an excellent question. Let's go back to a couple of slides here and see if we can come back to, is it this one? Yes, I think it's this one. Yes, it is. Okay. So when we talk about a control curve, we have to know 2 points in order for the software to find out where the curve needs to start and finish. So one of those data points is very easy because all of us know that we are selecting the pump at the design operating point. In this case, it happens to be 300 gallons per minute at 53 feet of head. However, we also need to know where it intersects the y-axis or the vertical axis, which we call it the control head. The control head, let's start with the control curve itself. The control curve is relatively flat at this part of the curve here. So the control head is virtually the same value as the pressure differential at minimum flow. So let's assume for a moment that my minimum flow in this case is 25 gallons per minute. Let's just kind of arbitrarily draw a line right there. And at 25 gallons per minute, the control curve is virtually flat or horizontal at that point, 25 gallons per minute. And so the control head is the same value, the pressure in this case, let's say that's 10, I'm just gonna make up a number and say that's roughly 12. So the control head in this case is 12 feet approximately. I'm reading it off my simplified chart here. That happens to be the same pressure differential at minimum flow. Now, when it comes to calculations, nearly all of us calculate the pressure drop at the design flow, but very few of us ever calculate the pressure drop, the 12 feet at minimum flow, MIN. In this case, the control head is essentially the same value. as the pressure drop at minimum flow, 12 feet at minimum flow. Hopefully that helps, Brett.
I think so.
If we don't have any immediate questions, I'd like to go into just a quick selection of a self-sensing pump to show.
Yeah, I think that's important. That's a good idea. Go ahead.
All right, yep. Okay, so I'm going to go to our website up here, Taco Comfort Solutions. This is our home page. On the left-hand side, I'm going to click on apps, and then a drop-down menu, go to pump selection. And over here is my selection for pumps. And it's 4 steps. In step 1, I decide the pump type. So let's go with self-sensing variable speed pump. And let's say that I had 1,000 gallons per minute at roughly 100 feet of head. And I'm going to leave the step 3 with these variables. And then I'm going to go to step 4. And let's say I want either an SKS, which is a split coupled vertical inline, or an SKV, which is a close coupled vertical inline. Let's see what the software says that's available. I kind of like this one here, just for the fun of it. Now, the default, I'm going to click on this. The default for the control head is 40% of the design head. So we at the factory, if you don't tell us what you want for control head, we will pick one, and we will pick it based on 40% of the design head. In this case, the design head is 100 feet. 40% of that is 40 feet. Now we can pick any value greater than 19 feet, because anything less than 19 feet results in a speed of less than 20 hertz, and we don't want the pump to drop below 20 hertz. So that looks like this on the pump curve. So there's the 40 feet. There is 1,000 gallons per minute at 100 feet of head. So this value up here is the design operating point, and this value over here is the control head. Now, if you notice how flat the curve is, for all practical purposes, between 0 and 200 gallons per minute, it's virtually flat at 40 feet. Fairly typical of this type of curve. Okay, so let's assume my minimum flow is 15% of my design flow. In this case, it would be approximately 150 gallons per minute. Well, there would be 100, 150, and that would be 40 feet. So if I did the calculation, if I calculated what the actual pressure drop would be at minimum flow, maybe if I was extremely accurate and I said, you know what, my flow is not going to be my pressure differential at minimum flow is not going to be 40 feet. It's actually going to be 30 feet. So it's going to be roughly 150 gallons per minute at 30 feet, which is the same as the control head. So I can actually go back here and put this in at 30 feet, and it's going to regenerate the curve. Now I have another curve where the control head is now at 30 feet. Did I do that correctly? Yes.
Yep.
It's 10, 20, 30, yes. And 150 gallons per minute. So now I'm much closer to the actual pressure drop at minimum flow. Now it turns out that this pump can use a function called ProBalance. ProBalance allows you, through a couple of keystrokes on the keypad, to find the actual pressure drop at the design flow. In this case, we estimated the pressure drop through calculations to be 50, in this case, 1,000 gallons per minute at 100 feet. What if in reality, it was 80 feet? Well, the pump can find that pressure drop at the design flow. And the way that's done is that through the building automation system, let's start with the pump itself. With the pump, you put the pump in constant flow of 1,000 gallons per minute, and through the building automation system, you ask all the control valves, two-way control valves, to go to nearly 100% open. Now, when I say nearly, you have to figure out what the diversity is in the system. If it happens to be a 80% diversity or 20% diversity, however you want to look at it, then you would command the valves to be roughly 80% open, and then the pump is going to find the actual pressure drop with the valves at their 80% open position. And then for minimum flow, let's assume in this case you had 150 gallons per minute, then again, you put it at a constant flow of 150 gallons per minute. It finds the actual pressure drop with all the valves closed with the exception of the three-way valves. And it'll find the actual pressure drop, in which case you can adjust the control head and you can adjust the design operating point, and you'll get a curve. I'm going to kind of grossly draw one in here. You'll get a curve perhaps that starts here, and it's actually, whoops, that's not the best thing, parallel with the other curve. And then this area inside here between these curves is the energy savings that takes place when you get more accurate data based on actual field conditions. So this was the curve from the factory, and then this is the actual curve that you want to operate the pump at. And the area between those two curves is the energy savings. So hopefully that answers some questions about control head, minimum pressure drop at minimum flow, and how you can use ProBalance to find the actual pressure drop at the design flow and the actual pressure drop at minimum flow. Good stuff, Brett.
Yes, excellent stuff.
Any other questions?
Zigzag. There's a couple of someone's asking, actually our good friend Veronica. Hi Veronica, I'm glad you're on. How does self-sensing,
what's up?
Veronica's located in Florida and takes care of a lot of our folks outside the US, South America. Anyways, how do self-sensing pumps work in parallel, and what do they need for it?
Well, self-sensing pumps in the short term, we have a modulating MPC, modulating pump controller. However, the modulating pump controller is on vacation, and the modulating pump controller, since it is on vacation, we are not providing self-sensing parallel pump control in the short term. When our modulating pump controller comes back from vacation, is all fresh from resting, has been out in the sun, it's got a nice suntan, and has a chance to rethink its position in the world, we will have the ability to have multiple self-sensing pumps operating in parallel. But as of today, our parallel pump controller is on vacation, and we don't have that capability in the short term.
Okay. There's a couple of questions pertaining to the location of the DP sensor, and I guess I'll ask them because we have a couple of minutes here. Although self-sensing pumps do not need DP sensors, have you ever designed a system with more than one DP sensor, like on a more complicated system?
Yes, it's a phenomenon that people use periodically. And they use multiple differential pressure sensors, and they take the most remote reading, and they have some kind of logic that they take one of those readings to control their pump. It's a bit sketchy because it's not clear which one of those DP sensors should be the right control signal. And that's one of the benefits of a self-sensing pump. It does not need DP, differential pressure transmitter location. It does it all through software. So it's not necessary to have that out there in the pump operating characteristics of a self-sensing pump.
Good stuff.
Good stuff.
Good stuff.
Yes. Any other questions?
Nope. I think that's pretty much it. Well, one person had a question for a while. Let's see. I referred to the bypass valve location. If it is closer to the chiller plant, would not you save pumping energy?
That's a great question. I prefer to have in a self-sensing pump, I prefer not to have a bypass. I prefer to have a three-way valve. The challenge with a bypass is that in a self-sensing pump, when you have a bypass for minimum flow, let's assume all the control valves in the system downstream have modulated to nearly closed position, and then the bypass begins to open. Well, the self-sensing pump cannot differentiate between a bypass measured using pressure differential and the simple control valve that's opening and closing. So as soon as the bypass begins to open, the pump begins to increase speed because it thinks it's a two-way valve somewhere in the system that's asking for more flow. So that's what I meant earlier. It's easier to use a three-way valve because you don't need any control logic. The three-way valve, let's say your minimum flow, we had a minute ago, we said 1,000 gallons per minute. Let's assume that the minimum flow is 150 gallons per minute. You just have to have enough three-way valves to equal 150 gallons per minute, and the system will operate properly. So if you're using a bypass, it's more complex. So to use a bypass, the recommendation is to use a flow meter to determine when to open the bypass, as opposed to a differential pressure transmitter. And so basically you're trying to maintain constant flow in the bypass versus the system, as opposed to constant pressure differential. Hope that answered.
I think it did. One person says, one last question. What is the lowest GPM? 20% of BEP?
The general recommendation is between 15 to 20% of the flow at the best efficiency point. So if your BEP flow, if you drop the vertical line from the BEP point on the pump curve, and let's say that came down to 1,000 gallons per minute, and the minimum flow wants to be between 15 to 20% of that value. Now, many times the minimum flow is driven not by the pump, but by the equipment in the system, either the chiller or the boiler or some combination of those two. So it becomes, I get that question all the time, what should I select for the minimum flow? Well, chances are the minimum flow, especially in a two-way valve system with chillers and boilers, is probably going to be dictated by the chiller or boiler. If it's a primary secondary loop and the self-sensing pump is on the secondary side, then essentially the minimum flow requirement for the chiller or the boiler is taken away from responsibility of the self-sensing pump. It's taken away from the self-sensing pump. It's no longer responsible for that. In which case, then the minimum flow it should be dictated by the pump, and in this case, between 15 to 20% of the flow at BEP. That was a mouthful, I know, but hopefully that helps.
I think it did. And guess what? We're over time. So great job, Rich.
Well, I'll say a couple of parting words. Thanks so much for participating in today's webinar. I'm going to turn it back to Brett. Be safe out there.
Thanks, Rich. Great job. Appreciate your detail, and a lot of great questions today, and you answered almost all of them. We'll have a couple that we'll have to follow up with. Again, folks, thank you for sitting with this series, 6 classes. 24 hours from now, you should be getting an email with a link to all 6 videos, as well as your 6 PDH credit hours. And again, if you have any issues with PDH credit hours, send in an email and we will work with you. So everybody, take care and stay safe, and signing off. Goodbye now.